Hello, today we will talk about Markov inequality and some corollaries of the inequality such as tail bounce behavior. First, let's look at the Markov inequality. We have a non-negative random variable x, and the inequality is that the probability that x is not less than t is bounded by the expectation of x divided by t provided that t is bigger than 0. And the proof is simple. We just move the t to the left side, and we use the probability density function f. We integrate the f from t to the infinity, and we extend it to the integration to the whole axis and get the expectation of x. And finally, we move the t to the right hand, and we get the Markov inequality. This is a very useful inequality in the field of applied probability. And then we see from the form of Markov inequality, we see that when the expectation is bounded, in asymptotic notation, we can see that the tail bound for the distribution function of x is equal to big O 1 over t. And next, we'll look at a corollary of Markov inequality, the Chebyshev inequality. We have also a non-negative random variable x, and we see that the probability that x is not less than expectation x plus t is bounded by the variance of x divided by t squared. We can use the same way as we proved the Markov inequality, and also we can treat this as a corollary of Markov inequality. We define a new random variable y equals to the square of x minus ex, and the probability that we want to derive is smaller than if we make square on both sides, and this is the probability that y is not less than t squared, and we use Markov inequality in this place, and we get that it is bounded by the expectation of y divided by t squared, and this expectation of y is just the variance of x. So we proved the Chebyshev inequality. From this form, we see that when the variance of x is bounded, the asymptotic behavior of tail bound is big O 1 over t squared. We proved the tail bound, but we also see that the condition is stronger. In general, if the nth order moment of x is bounded, we have that the tail bound of the distribution function of x is equal to the big O 1 over t to the n. So next, we could say that if any order moment of x is bounded, could we have a stronger tail bound for the random variable x? That is the Chernoff bound. So, for example, if we have if the e to the x, the expectation of e to x is bounded, we define ya equals to e to the ax, where a is bigger than 0, and we assume that this expectation is bounded so that the every order moments are bounded, and we define ca equals to the logarithm of the expectation of a. Then we apply the Markov inequality and get that the probability that x is bigger than t equals to our exponential expression in terms of t. And we want to get the best bound in this form, so we minimize the right hand side, and we just take the first order derivatives and make it equals to 0. So we get that at the optimal point A star, the phi prime is equal to t, and at this point we get the best Chernoff bound. It is exponential bound. Here we give a short example, random walk. If we have a random walk Sn equals to the sum of IDD random variables, we define x equals to e to a Sn, and we define similarly the function phi and c. And from the Markov inequality, we have that the random walk, the tail behavioral random walk is bounded by phi a e to the minus at for every a, and we just make the first order condition holds, and we get the optimal selection of a. And for large n, if the random walk continues, for large n, we just make that the phi sub z prime a star is 0. And in this way we get the Chernoff bound for the random walk. Today we will stop here and see you next time. Thanks